Today's topic is nucleophilic addition reactions of aldehydes and ketones. Myself, Dr. Digna Varghese. Nucleophilic addition reactions of aldehydes and ketones. Here you can see in aldehyde and ketone, the carbonyl group is present. The carbon-oxygen double bond of the carbonyl group is polar because the oxygen atom is more electronegative when compared to carbon. So the electron from the bond is shifted more towards oxygen atom. So it acquires a partial negative charge. So that oxygen is delta minus. But carbon atom is the electron deficient one. So it acquires a positive charge, that is it is electron deficient compound and also carbon, or it is an electrophilic one. That means it is an electron loving species. Okay, so therefore the nucleophilic reagents, nucleophile means the nucleus loving species. Nucleophile has a negative charge, so it always searching the positive part of the compounds, and it attacks towards the positive part of the carbonyl carbon. Okay, so the nucleophilic reagents can attack to the group. Okay, so in carbonyl carbon, the carbon acquires a positive charge due to the high electronegative oxygen atom. So towards carbon, the nucleophile can attack. Thus, aldehydes and ketones undergo nucleophilic addition reactions. In organic chemistry, a nucleophilic addition reaction is an addition reaction where a chemical compound with an electrophilic double or triple bond reacts with a nucleophile such that a double or triple bond is broken. Okay. Mechanism of nucleophilic addition reactions of aldehydes and ketones. Here you can see the mechanism, the general mechanism of nucleophilic addition at the carbonyl group, which involves two steps. In step 1, the nucleophile, that is Nu minus, attacks to the electron deficient sp2 carbon of the polar carbonyl group. We know carbonyl group is polar due to the electron shift towards the oxygen atom. So oxygen atom acquires a partial negative charge and carbon atom acquires a partial positive charge. Due to this polarity, the carbon atom is electron deficient, or which is electrophilic. So the nucleophile, which has a negative charge, it attacks those species which has positive charge. So the nucleophile can attack to the carbonyl carbon. So the sp2 carbon atom changes to sp3 carbon atom. Here you can see this is a planar group. Towards this a nucleophile attacks. After the addition of a nucleophile to the carbonyl carbon, the sp2 carbon becomes sp3 and thereby yields a tetrahedral structure or alkoxide intermediate. In step 2, this alkoxide intermediate reacts with H plus in the reaction medium, that is NuH. Here the H plus from the reaction medium that will attach to the alkoxide and forming an alcoholic or hydroxyl group. Okay, so this is the addition product. This is the nucleophilic addition product. The mechanism again tells here the nucleophile, which has a negative charge, attacks to the carbonyl group CO, which is slightly positive due to the electronegative oxygen atom. The electrons shifted to oxygen atom, and here the nucleophile attacks to the carbonyl carbon. The planar carbonyl compound becomes tetrahedral, forms a tetrahedral intermediate due to the addition of nucleophile. The sp2 becomes sp3 carbon. The alkoxide group oxygen atom, which attacks the H plus from the reaction medium and forms a adduct, that is the product of nucleophilic addition reaction. What about the order of reactivity? That means nucleophilic attack is favor in aldehyde or in ketone more. Here you can see a ketone which attacks by a nucleophile. Nucleophile attacks to the carbonyl carbon and it forms a sp3 tetrahedral intermediate, alkoxide intermediate, which will react with H plus and forming the adduct. In the case of aldehyde, the R group is replaced by hydrogen here, but the same mechanism happens here. The nucleophile attacks to the carbonyl carbon and forming the sp3 tetrahedral alkoxide intermediate. This will attacks the H plus from the reaction medium and forms the adduct. Here you can see the approach of the nucleophile to the carbonyl carbon is sterically hindered in the case of ketone. Here you can see two alkyl groups are present. Instead of ketone in aldehyde, here one hydrogen in place of this alkyl group. So it is steric effect is less here in the case of aldehyde when compared to ketone. Due to the electron releasing nature of each alkyl group in the case of ketone, the electrophilicity of carbonyl group is more decreased in ketones than in aldehydes. Here you can see the carbonyl carbon is positive charge while the alkyl groups are electron releasing due to plus I effect. So the electrophilicity, electron loving nature of this particular carbon, carbonyl carbon, is less when compared to aldehyde because here only one alkyl group, electron releasing alkyl group is present. So the electrophilicity is more towards or more in this carbonyl carbon when compared to ketone. Okay. Other important explanation is that the in ketone, the original compound is trigonal planar with the bond angle is 120 degree with regard to carbonyl group. But in that case of transition state, it will be converted to sp2 to sp3 hybridization and the bond angle is 109.5 degree. So the bond angle is decreased here. For this reason, the alkyl groups are more closer towards this carbonyl carbon and the nucleophile is also attached to this. So this the transition state for a ketone, thereby the alkyl groups are more closer when compared to the original ketone. As a result, as compared to the transition state for an aldehyde here, that for a ketone is less stable due to greater steric crowding. Here it is less stable, but it is more stable. Okay. So The nucleophilic attack is easier in the case of aldehydes when compared to ketone. So you can see here the formaldehyde is more reactive towards nucleophilic addition reactions when compared to other aldehydes, which is more reactive when compared to ketones. Examples for nucleophilic addition reactions. Here you can see addition of HCN. The acetaldehyde reacts with HCN and forming acetyl cyanohydrin. The mechanism of the reaction is that in step 1, the attack of the nucleophile Cn- towards the carbonyl carbon and forming the tetrahedral alkoxide intermediate. In step 2, the addition compound reacts with the H plus in the reaction medium and forms cyanohydrin or acetyl cyanohydrin. So this is the mechanism. So the acetaldehyde reacts with HCN. It forms the Cn minus, attacks to the carbonyl carbon, and the oxygen will get a negative charge which will react with the reaction H plus from the reaction medium and forming the acetyl cyanohydrin. Other examples of nucleophilic addition reaction using HCN, the acetone reacts with HCN and forming acetone cyanohydrin. Here you can see the Cn minus, that is the nucleophile, which is attached to the CO carbonyl carbon and forming an alkoxide which will react with in next step with the H plus of the reaction medium. So it will forms acetone cyanohydrin. Next example is benzaldehyde that will reacts with HCN. Here the negative charge cyanide ion attacks to the positive part of the carbonyl carbon and forming an alkoxide intermediate which will attacks the H plus from the reaction medium and forms the addition product, that is the benzaldehyde cyanohydrin. Here you can see the addition of sodium bisulfite or sodium hydrogen sulfate. Here you can see the Na plus HSO3 minus which will attacks the negative part of the HSO3 minus which will attacks to the CO part and forming an alkoxide intermediate, that is SO3H here and O minus Na. Here the proton transfer occurs in next step and forming OH and SO3Na. So this is the addition product of sodium bisulfite. Here you can see acetone reacts with sodium bisulfite. Negative charge here, positive charge here. First HSO3 minus attached to the carbonyl carbon and forms a alkoxide ion which will attack the Na plus of the reaction medium which will undergo proton transfer like this and forming the addition product. Next example is acetaldehyde reacts with sodium bisulfite. So the negative part is attached to the carbonyl carbon and forming an alkoxide sodium alkoxide. That alkoxide reacts with the sodium plus of the reaction medium and forming sodium alkoxide, which will undergo proton transfer and forming acetaldehyde bisulfite addition product. Addition to carbonyl groups. Here you can see some other examples of nucleophilic addition reactions. With a carbonyl compound as an electrophile, the nucleophile can be water in hydration to a geminal diol that forms hydrate, an alcohol in acetalization to an acetal, a hydride in reduction to an alcohol, an amine with formaldehyde and a carbonyl compound in Mannich reaction, an enolate ion in an aldol reaction or Baylis-Hillman reaction, an organometallic nucleophile in the Grignard reaction or the related Barbier reaction or a Reformatsky reaction. Light such as Wittig reaction or the Corey-Tchaikovsky reagent or alpha-silyl carbanions in the Petersen-Olfnation reaction, a phosphonate carbanion in the Horner-Wadsworth-Emmons reaction, a pyridine zwitterion in the Hammett reaction, an acetylide in alkylation reactions, a cyanide ion in cyanohydrin reactions. In our syllabus, there is only two examples for the nucleophilic addition reactions of aldehydes and ketones, that is addition of HCN and addition of sodium bisulfite. For your attention.